It's not perfect. Okay, we're at the tail end of the day. 2 more presentations to go, and the first of those is by Jens Freiman.
Yes.
On Virtio 1.1, what's new in the next version?
Okay. Hi, everyone. Can you hear me? Okay. So, yes, my name is Jens Freiman. I work for Red Hat. And this talk is about the recent Virtio work that we've been doing on extending the Virtio specification. So the goal is to extend Virtio in a way to improve its performance and also to make it work better with workloads that it currently doesn't support very well. So I'll give a very, very brief explanation of Virtio and just put it into context to NFV very shortly. Before talking about the main new topic in Virtio 1.1, which is a feature called packed virtues. And eventually, if time allows, I will talk about a few other developments in the space of Virtio that I think are worth mentioning here to this crowd. But first, let's start with what Virtio actually is. So Virtio is an abstraction layer for devices and hypervisors, and the idea is to have a common framework for I/O virtualization. And at its core, it defines virtual queues, also a way to configure devices, and mechanisms for backward compatibility. Virtio is quite good at that. So there are many different devices. There are Virtio net, block, console, and so on. And to guess, these devices appear as normal PCI devices, or if you're on a mainframe, as channel devices. Good. So, and to put this into context to NFV, so where in a possible NFV setup is Virtio used? And I really just picked a random example. Let's say you're using a DPDK-based application in your VM. And then you have a Virtio front end in the guest, and you have a Virtio backend in the host. In this case, Virtio is part of the DPDK library, and in the host, it's part of the host user, in this case, also part of DPDK. And by the way, I guess most people are familiar with DPDK, but this is like a library and provides user-space drivers and libraries to build fast packaging, package processing applications. So yeah, this is the part. Talking about the Virtio architecture, at the top you see the device-specific components. This has everything that's specific to Virtio net, block, and so on. At the bottom you have the transport-specific parts. As I said, devices can be PCI devices. They can be also CCW devices. That's for mainframes. But I want to talk about the Virtio part today. So we want to add a new kind of virtues. And so why do we want to do this? The way virtues are defined until Virtio 1.0, and I'll call them split virtues from now on, as opposed to packed virtues. They're not really fit for a straightforward implementation in hardware. So I've been expecting hardware support for Virtio for quite a while, actually, and it never happened. And well, I guess it's just because they're too complicated to implement. I know that one company once tried it and stopped at some point. And now there are several companies that make an effort to push forward in this space and actually try implementing Virtio in hardware and make accelerators for it. But not also hardware, also pure software implementation should benefit from Virtio 1.1 and the packed ring layout. So what's the problem with the old way of virtues, with split virtues? So this is what the data structures of it look like. So first, each request is stored in a buffer in memory shared between the driver and the device. The buffer address and length are stored in the 16-byte descriptors, and they are stored in a descriptor table. Now, if the buffer is not contiguous, then multiple descriptors can be chained together by setting a next field in the descriptor. So where in the table to put each descriptor, that's up to the driver. And a request is identified by a head index, which is a 16-bit offset of the first descriptor in the table. Now, head indices are stored in the available ring. And to signal to the device which indices are valid, the driver also maintains an available index in shared memory. And after executing the request, the device will store the head index in this used ring, which is also in shared memory. It also stores the length of the used part of the buffer, and it then increments the used index value in the shared memory to signal to the driver that this descriptor has been used. And so fundamentally, what we see is that host and guest communicate by passing messages between CPUs using shared memory. And how do CPUs do this? So at a very low level, when a CPU accesses memory that is also modified by another CPU, this will cause the CPU to synchronize their caches. And they do this by exchanging cache coherence protocol messages. So basically, they speak to each other. For example, for some architectures, when a CPU accesses memory that was previously accessed by another CPU, this will also cause a cache miss. And while the number of these cache coherence messages exchanged and cache misses directly impact the communication latency. Now, let's count cache misses when using VirtIO 1.0. The queue consists of 5 parts, and as a buffer moves between host and guest, each of these parts is read and written at least once. So this is implying at least 5 cache misses per buffer, if no batching is allowed. If we batch, then it gets a little bit better, but not too much. So what can we do to reduce the overhead? So the issue is that the information for this request is spread over multiple data structures, and this is causing multiple cache misses. So to reduce the overhead, we should pack as much information as possible into a single data structure. And what follows is a proposal to do exactly that. This is currently being discussed on the VirtIO mailing list, and there's a prototype for DPDK also on the DPDK mailing list. We're working on QEMU and Linux as well, but DPDK prototype was there first. We started with DPDK. And so what we do is we get rid of the available and used string and the index structures completely. And what we do instead is we make the guest write descriptors out in descriptor ring order and in our new descriptor ring. So within each descriptor, we add 3 new fields or flags. An available bit, a used bit, and a descriptor ID. Then to make buffers available to the host, the guest will write them into descriptors in our new ring. And then it will flip the available bit. This implies that it's now OK for the host to consume this descriptor. And the host can then process them in any order. Each descriptor also has an ID field, as I mentioned. And after processing, the host writes the processed descriptor ID back into the ring, and it flips the used bit. And by this, it's telling the guest that an entry has been used, and then that the guest can use this again, or can make it available again. So device and driver are also expected to maintain internally, not in shared memory, a single bit counter. And so starting at 1 and changing value each time, the last descriptor in the ring is accessed. It has to be flipped when the last one is accessed. And as I just mentioned, these bits are passed as available and used bit in the descriptors. So assuming that the ring is 0 initialized, on the first iteration over the ring, to mark the script as available, the available bit is set to 1. And then on the next iteration, it is set to 0, and so on. Similarly, to mark a descriptor as used, the used bit is set by the device on the first iteration to 1, 0 on the second one, and so on. So what do we get by these counters? Well, flipping the counter values allows the host and guest to detect new available descriptors even after the ring has stopped. Because it could be that some descriptors were not touched in one pass of the ring because we skipped them. And this way we will know that this descriptor was made available and is currently to be used. So, as I said, we have an implementation, and I was measuring performance according to RC2544. It was done on Intel-based servers. Host and guest on the device on a test were running RHEL 7.4. At the time, the patches were based on DPDK version 17.11, and the patches are now available on GitHub and hopefully soon also upstream. So apart from micro benchmarks, this is the only real test run I managed to do before this talk. So with 64-byte packets, we measured a boost from 18.8 to 22.6 Mbps. And well, this is using slow NICs, so larger packets simply hit wire speed on the setup. And I'm working on benchmarking with larger packets. So if someone is here familiar with T-Rex and in combination with XL7010 Intel NICs, then please talk to me. I have some questions. Yeah. So I think we can conclude that Virtios as defined in 1.0 are not an optimal data structure for host-to-guest communication, and also not perfectly defined for an easy implementation in hardware. And we're trying to make this better with Virtio 1.1. Well, by the way, if you want to participate in Virtio or work on a Virtio specification, or you have a new feature that you want to add, you have a new device that you want to add, this is actually quite easy and also fun. You basically just download the specification source from GitHub. You edit it, it's LaTeX, so you have to build it, compile it, and look there to make sure it looks right. And once you've done this, you basically just subscribe to this Virtio common mailing list. You have to reply to confirm your subscription, and then you can send your actual, sometimes it's a one-liner patch to reserve just a feature bit. You send it to the mailing list, and if everyone's okay with it, then you send another mail and ask for a ballot. This ballot will run for a week, and after 2 weeks, if all goes well, your feature is in the specification. Good. So that's the part of my talk where I wanted to, I was going to talk about the Virtio specification. Now I have actually two things that I wanted to mention that I think are interesting. So one thing is a project initiated by Intel, vDPA. It's called Virtual Datapath Accelerator. And well, so Virtio as a para-virtualized device, decouples your VM and your physical devices, and that's nice in cloud environments because you can easily live migrate them and so on. But in terms of north-south traffic, that doesn't compare to, for example, an SR-IOV device, obviously. Now, this picture here, which is probably not easy to read, it shows how it looks without an accelerator device. And Intel is now working on a framework to make it easier to use a Virtio accelerator device. So essentially, this will allow you to use hardware that can write and read the Virtio vRing format, and it will get you basically SR-IOV-like performance and the data path. And the way they did this will also make it easier to basically switch from a setup where you just use normal Virtio to one that that's actually using an accelerator device. So this picture includes the accelerator device, and as you can see, the control path is still emulated, but this is not a bad thing because it's not performance critical. But the data path is now handled by this hardware device, and that can write directly into the VRing. Yeah, with traditional I/O, you would usually do packet I/O via shared memory and interrupts via IOQFDs and kicks doorbell via IO event FDs. Backend then would be usually vhost, kernel, or user. But with vDPA, that's a bit different. You have the doorbell kick, and this could be, depending on your guest, either port I/O based, or if you have a newer guest, then would be MMIO mapped. Interrupt notification here is done via VFIO interrupts, like in pass-through devices. And as I said, NQ-DQ to the relink is done with the accelerator device. It's also using VFIO MDEF for address space access into DVM. And the control path is set up by vhost user protocol messages, basically. Also worth mentioning that here it's currently not using virtual IO MMU, but that's something we're looking into that should be improved. So while you might ask, if you have a VirtIO capable device, why don't you just pass through the entire device to the guest? And well, there's several reasons why you might not want to do this. And one is that VirtIO is a growing spec, and things evolve in step, and a hardware implementation would have to keep up with the spec all the time. It's kind of unlikely. Also, physical functions have a lot more features and metadata and so on that a virtual function doesn't really need to care about. You would inherit all the pass-through properties, and that includes also it's harder to live migrate without having vendor-specific solutions. So yeah, for example, in VirtIO 095, you couldn't really pass through a device to the guest because all the register-based access was port I/O based. And eventually, the major reason is that the nice thing about VirtIO is that you have a front end and a back end, and that's decoupled, and you can combine things. So the front end is often rather static, but in the back end, it's more common to have a choice of the actual VirtIO backend. Okay, this is another project that's currently in the works. It's also started by Intel, and this is more about efficient east-west communication between virtual machines. So imagine you have a set of virtual network functions, like, I don't know, a firewall, intrusion detection system, router, whatever, and they need to forward packets to each other. You would usually put them into a virtual switch in the host, and then packets gather there and are transferred one by one or to the target VM. And the downside here is that you have like a long code path, and it doesn't always scale very well. But what if instead you could send packets directly from to the target VM without having the data path going through the host? Code paths would be shorter, and it would be also easier to scale. Now, the way this works here is that they have introduced a new set of vhost PCI devices that you have in the VMs, and also a vhost PCI server as a central component in one of the VMs. And they are connected via Unix sockets, and they speak the existing vhost user protocol over that to set things up. So there's a presentation from KVM forum about this. There's also a recorded video on YouTube if you're more interested in this. The current status is that there are patches on the mailing list, and they are being discussed. There are still some design discussions, and so the thing was that the way they wanted to do this would also introduce a lot of code duplication, especially in the vhost user part. So Stefan Heinocci suggested that they could use something similar. And okay, So VirtIO devices usually were just, you had your driver and a guest, and you had an emulated device in QEMU in a host user space process. And then as it evolved, you had, so vhost came along, which kind of allowed you to implement part of the VirtIO backend in the kernel and user space. And then the next thing was actually vhost user, which would allow you to implement this backend in a user space process in the host. Now, VirtIO vhost user is kind of taking this even one step further by moving the vhost device backend into the guest. And it works by tunneling the vhost user protocol over a new VirtIO device type, which is called VirtIO vhost user. So yeah, the following diagram will show this. So in this diagram, VM2 sees a regular VirtIO net device. VM2's QEMU uses the existing vhost user feature, like if it were talking to a host user space, vhost user backend. And then virtual machine 1's QEMU will tunnel the vhost user protocol messages from VM1's QEMU to the new VirtIO vhost user device, so that guest software in VM1 can act as the vhost user backend. Now, it's possible to reuse existing the vhost user backend software with VirtIO user, since they use the same protocol, right? Now, a driver is required here for the VirtIO vhost user PCI device. So that code has to be written for that as well. And the vhost device backend vrings, they are accessed through shared memory and do not require vhost user messages to be exchanged in a data path. So no VM exits are taken here. When poll mode is used, of course, not at all. But even when interrupts are used, then QEMU is not involved here because we can use the lightweight IO event FD VM exits. Yeah. So Java can be implemented in the guest user space process using Linux VFIO PCI, but also guest kernel driver implementation would be possible. Also, the vhost device backend vrings, as I said, they are accessed just using shared memory. It's also worth pointing out that this works for net devices, block devices, SCSI, and so on. Another thing, I think I might skip this here. How much time do we have left?
A little over 5 minutes.
Okay, then I might just skip this. Or one sentence. So this is just a new idea to do transparent bonding in a guest by without having complex configuration by the user. So the idea is to just have a VirtIO device that has a special feature flag. And if this feature flag is seen in a guest, then we can go and look for another SR-IOV device that we can bond with. And then we could have always used the fast data path over the SR-IOV device. And for migration, we could just put the link of the SR-IOV device down and then switch over to a VirtIO device, do a migration, and on the target system see, is there another capable SR-IOV device that we can use for data path? And if not, we could just use the VirtIO device. So, yeah. Conclusion of my talk. So VirtIO 1.1 will be a rather big release. There will be many changes, mostly for the packed Virtues, but also some other things required for hardware implementations. It's worth taking a look. DPDK implementation is available. I didn't put the link in here, but it was in a previous slide, so you can look it up there. Also, if you're interested in this and in participating, we have like a monthly meeting, a monthly call, where we discuss these things, VirtIO 1.1, but also other VirtIO features. You're welcome to join. Just contact me. There's quite a few companies already involved. and new ones are always welcome. So that's the end of my talk, basically. Are there any questions? There's one. Yes. So the question was, the implementation of Virtio 1.1 will require changes to QEMU, and what's the timeline for that? So right now, the next target is to get things upstream in DPDK, and we're at the moment already started to work on the Virtio implementation. So as a few months from here.
Any other questions?
Okay, then. Thank you.
Okay. Thank you, Jens. So, last talk of the day coming up now. In just a few minutes with Pablo Camarillo. I hope I pronounced that right. On segment routing v6 with VPP. Hi, Pablo. Nice to meet you.
Nice to meet you. So we are actually two speakers. So it's Hamid and me.
Oh,
Hamid is going to explain Linux and I'm going to explain VPP.
Okay.
Start plugging this in. You may have to turn your resolution down.
Can we have them both? Yeah. Is it working? HDMI cable.
And when you plug it in, just give it a lot of time. Oh, you need an adapter? You don't have a
No, it's the Steve new Mac.
Okay.
Yeah.
Okay, it's working fine.
Yeah, there we go. Great.
Before you start the talk, may I have the microphone?
Just for those leaving, one last reminder that we have a meetup a little bit later for the SDN NFV dev room in the Mannequin Plus Café, which is Rue des Grandes Carmes, I think, around 7:30. So you're welcome to join us. Thank you.
I'll warn you guys, only have 15 minutes, 10 minutes. You can use the full 30 if you want, if you don't want to take any questions. But so whatever I tell you, that's when the end of your 30 minutes.
Okay. Thank you very much.
Okay, so good afternoon, everyone. Last talk of the day, and then you can go for beers. So this is my colleague Ahmed. He's a PhD student from Italy, and I'm a software engineer at Cisco working in the segment routing architecture team. And today I'm here to talk about segment routing, which is something quite different from all the talks that we've been seeing today, because all of them were focusing on different platforms, and this one, what is focusing is on the actual protocols on the network, actually on SP networks. So what I'll try to do is give you a brief overview of segment routing, the deployment use cases, and then talk a bit about BBP, Linux, and Sarah, which you will see later what it actually is. So what is segment routing? The idea behind segment routing is that we actually leverage the paradigm of source routing. So what does this mean? That instead of programming all the routers in the network, what we are actually doing is that on the head end, we are actually adding the list of segments that a packet has to traverse through the network. So what this means is that if I want to go from Madrid to Amsterdam via Brussels, what I just need to do is when my packet is out from Madrid, I just add one little segment that is saying Brussels and then Amsterdam, and the packet will follow the shortest path to Brussels and then it will go to Amsterdam. That's simple. And this is actually really scalable, because what this means is that you can implement any traffic engineering policy that you want, and you can actually put this together with any NFV deployment that you want. And actually one of the main benefits is that we can have policies end-to-end. So starting from the data center and traversing the entire network through the metro and one. So we have two data plane instantiations. One of them is MPLS and the other one is IPv6. So in MPLS what we are just doing is one segment is one MPLS label and that's it. The second instantiation is IPv6. So in IPv6 what we are doing is we are using an IPv6 routing extension header, which it was defined 15 years ago, and we have one segment is one IPv6.